Hello, geometry folks. Today we are going to be talking about similar figures and what it means to be similar. And we've touched on it a little bit, but now we're going to be starting a whole new unit on similar figures. So what you're going to need is your calculator, pen or pencil, and your notes. You do not need a foldable for this one. So let's start off by thinking about similarity as a concept, conceptually. If I tried to place this shape into a copy machine and reduce it, this shape would obviously not be an output. This one wouldn't be an output, but this one would, right? It's just a miniature version of whatever I put in there. So remember when we talked about dilations in geometry and transformations? That's what it means to create similar figures, is stretching or shrinking the image and keeping the relationship between sides and angles. So you don't need to put this in your notes, but we're still just talking concepts. To make a smaller or larger version of an image, you do not change the angles. You do not add or subtract from each side. The only thing that works is to divide or multiply by a certain number, and that number is what keeps the shape proportional, which is what we were talking about the last couple of days in class. So now's the time you want to grab out your pencil and write this definition in your notes. This is the definition of similar and what it means to be similar. So polygons are similar if their corresponding angles are congruent and the ratio of their corresponding sides are in proportion or are in equal ratios. Remember, a proportion is an equation with two ratios equal to each other. So if two polygons are similar, then the ratio of the length of two corresponding sides is called a scale factor. Remember, we talked about scale factors when we did dilations in our transformation unit. So it's that number that we multiply by in dilations to get it bigger or smaller. And now that's going to be our proportion to create things similar. Okay, so in this first example, I do want you to write this down in your notes. That's why we have the pencil on the page. Remember, whatever page has the pencil is the stuff you need to get in your notes, and every other slide is optional. So if you want to take a second to draw these images, you can. So we are trying to determine if these two shapes are similar. So the first thing that I need to notice is that all the angles are congruent. And in here we have corresponding angles congruent. So now we have to see if corresponding sides have a constant or the same ratio between them. So I'm just going to start on the top, and so 6 compares with 4, those two sides, so that's going to be my first ratio, 6 over 4. And then I also have 9, and that compares to 6, so now my second ratio is going to be 9 to 6, or 9 over 6. And then we have 12 to 8, and then last but not least, 15 to 10. And we always want to write ratios in the simplest form. So we can take out a 3 of the 6 and 4 and get 3 halves. We can take out a 3 of 9 and 6 and still get 3 halves. We can take out a 4 for 12 with 12 over 8, which is 3 halves. And then we also can take out a 5 out of 5 and 15 and 10, excuse me, which is 3 halves. So this 3 halves is the same between all the relationships of the 4 sides of this quadrilateral. So because it's the same number, the two figures are similar. So our scale factor then is also this number or this ratio that we found in simplest form. So our scale factor is 3 halves. And just like we had for congruence, we had a congruence statement. Now we're going to have a similarity statement. So I'm going to say quadrilateral X, Y, Z, W is similar. This means similar to, if you want to mark that this symbol means similar to, quadrilateral Q, R, S, and P. So this example you don't need to write in your notes, but we can just talk about it. So I'm going to start off with the shortest side. So the shortest side in the first figure will be 10.5 and 4. So I'm going to write that as a ratio, 10.5 over 4. That would be my first ratio. The second ratio would be 12 over 9, because that's the second biggest sides of the two triangles. And then last but not least, 18 over 12. Well, for 18 and 12, I can simplify that fraction by taking out a 6 out of both. So that brings me to 3/2, just like the last example. And then for 12 divided by 9, we can take out a 3 out of both, which gives me 4/3. 4/3 is not the same thing as 3/2. So this figure is not similar. It would have been similar had we gotten the same ratio between all the relationships of the three sides. So you don't have to write this in your notes, but let's see if these two rectangles are similar. So I'm going to pick the shortest side, 8 and 3. So that'll be my first ratio, 8/3. And then 15/10. Well, 8/3 can't be simplified as a fraction, but 15/10 can be simplified as a fraction, and that becomes 5/2. 5/2 is not the same thing as 8/3, so this is not similar. So this is the second example I want you to get into your notes. In this example, we've been given that the trapezoid TUVW is similar to trapezoid ABCD. So now we know that the two are similar, and we can use our knowledge of similar figures to answer the following three questions. So the first question is asking to find the scale factor of the bigger trapezoid to the smaller trapezoid, TUV to ABCD. So we have to pick a pair of sides that are corresponding to each other. So I'm just going to pick the top 9 and 15 that we want to set up as a ratio. So we wanted to write the trapezoid TUVW to ABCD. So because I'm referring to the first side length in my bigger trapezoid, I have to write that one first. 15/2, and you can write this as a fraction or as a ratio is as a fraction or with a colon, and then the side that corresponds, which is the side length AB of our other trapezoid. So it's 15/9. And we always want to write our scale factors or our ratios in simplest form. So we can divide out a 3 both out of 15 and 9, so that's 5/3. So that's my answer for that one. Now it's asking us to find the length of TW, which is this side length right here. And I'm going to let this side length be represented by the variable x because that's the side length I'm trying to solve for. So we have been given a ratio between the two sides, and we could set up another one into an equation to get a proportion. So it doesn't matter which one goes on top, but I'm just going to keep the same ratio we had in the first examples or in the first problem. So 15/9 is equal to x to 6. And all we have to do from here is just cross multiply. So we cross multiply this and we cross multiply that. Well, 15 times 6 is 90, and 9 times x is 9x. We get 90 is equal to 9x, divide both sides by 9. X then would be 10. So this side length here is 10. Now they're asking us to find the measure of angle TUV, which is this angle right here. It's angle U on our larger trapezoid. So remember we said when two figures are similar, all of their angle measures are equal. So U corresponds to angle B in our other trapezoid. So these two trapezoid angles, U and B, are congruent. We also know that from our previous unit with parallel lines, when we have two parallel lines like we do here and like we do here, we can form angle relationships. Remember we had alternate interior, alternate exterior corresponding and same side interior. If we wanted to look at these two parallel lines and this transversal, this angle and this angle are on the same side of the transversal, both lying on the inside of the parallel lines. So these are same side interior angles. And remember, the same side interior angles are the only pair of angles that don't add up to 180 degrees, that aren't congruent, they add up to 180 degrees, excuse me. So we have 180 degrees is equal to 70, let's say plus x for our other angle over here. So we also know that this angle down here is 70 degrees because this angle corresponds to this angle. B corresponds to angle C. So we can set up an equation. 180 is equal to 70 plus x. Subtract 70 from both sides, and we get x is equal to 110 degrees, or angle TUV, which is what they were asking me, is equal to 110 degrees. I want to make sure that the measure of angle TUV is equal to 110 degrees. So this is my final answer. Whenever we're trying to find the measure of angles, I should have said this at the beginning, we don't use our proportion. We can't use our proportion. We just know that because the two images are similar, that these angles are in fact congruent. All right, so this is the third example I want you to get into your notes. So if you want to take a second to pause the video and draw, that's totally fine. But we are trying to find the value of x. We have been given that the triangle, the small triangle CED, this entire triangle, CDE, is similar to FGH. So with that, we are going to use that information in order to solve for x. One thing I'm going to point out is this line right here from D and G to the base of the two triangles. This is called the altitude or the height of the triangle, which you might remember from taking areas of triangles, but that's when we have from the top angle to the base at a 90-degree angle, that is the altitude of the two triangles. So those are also, the altitude is also in proportion to the sides, just like the sides are proportional when the two images are similar, which brings up a really good point. If two polygons are similar, altitudes, medians, diagonals, angle bisectors, and perimeters are also in the same ratio. So take a second to write that down and make sure you don't forget this. Star it or circle it or put a cloud around it, whatever you need to do to remember that not only are the sides of images proportional, but other lines that we can draw on those images like altitudes, medians, diagonals, all those things are also in that same proportion. So with that in mind, we can start solving right away. So we want to set up our two ratios. So I'm going to start with 7x over 9x. That's the small triangle in reference to the larger triangle, and we keep in the same ratio the altitude measures or expressions. And then we do 8x minus 1 over 10x plus 1 because we can do the small triangle to the big triangle just like we did on our first ratio. So now we have a proportion and all we have to do is cross multiply. So 7x times the entire quantity, 10x plus 1, is equal to 9x times the entire expression or quantity, 8x minus 1. That gives me a 70x squared plus 7x is equal to 72x squared minus 9x. And see, we can see that we have a squared term here, so we're going to have two answers, and we're definitely going to have to factor. So remember, when we want to factor, we have to set some side equal to 0. So I'm just going to subtract everything away from the left side, and whatever you do to one side, we have to do to the other. So everything on my left side went away. So 0 is equal to 2x squared minus 16x. Well, I'm going to rewrite that up here. 0 is equal to 2x squared minus 16x. What do we have in common between the two terms, 2x squared and negative 16x? We have a 2 in common, and we also have a x term in common. So if I were to take out a 2x from the first term, that leaves me with an x. And if I were to take out a 2x from the second term, that would leave me with a negative 8. So we have a product with two factors equal to 0. Now we can set both of our factors equal to 0 separately and solve for x separately. So 0 is equal to 2x, and x minus 8 is equal to 0. Here, x would be 0. We divide by 2 on both sides. Here we add 8 to both sides. X is equal to 8. Normally, we would say that those are both of our solutions, but here we're given a context of a triangle. Think about if x were to be 0 here. 7 times 0 is 0, meaning that the altitude of this triangle would be 0, which would be a flat line. And then here would be the same thing, 0 altitude, which would make this fall into a flat line. So we know that that's not realistic for our image. So our answer is x is equal to 8. I want to thank you guys for taking good notes, and I will see you when I get back.